Hello, and welcome everybody. Thank you very much for coming to this session. I hope that you are here not because you are in the wrong room, but because you are interested in application security and securing the software. Because the reality is that developers have not learned about secure coding or crypto in school. At university level, secure coding or software security is not part of the curriculum in most universities. At the same time, cyber attacks are a real and growing threat to businesses. An increasing number of these attacks takes place at the application layer. The best defense for this is to develop the software where security has been incorporated as part of the software development cycle. The OWASP of them proactive controls consider security as part of the software development cycle. How many of you have heard of OWASP proactive controls? Okay, a few hands up. That's very good. In this presentation, I will go through these security techniques that you can use while writing the code, and for each of these controls, we are also going to explore which of the most common vulnerabilities or software risks you can prevent. My name is Katy, Anton, and I come from a software development background where I have led and created teams of developers. In my previous job, I was asked to take care of this thing called security, and this is when I started looking into security and incorporating security as part of the software development cycle. I then joined the OWASP of them proactive controls as contributor and then later as project co-leader. I currently work as application security consultant at Encode, a business unit within CE Technologies, where I advise developers around the world on how to secure their software. The OWASP Top 10 Risks is by far the most cited OWASP document, and this presentation will be tied in with the most recent version of this, which is the OWASP Top 10 2017, a release candidate. So you are the first one to have the security controls presented on how to defend these vulnerabilities found in software applications. But how many of you have tried starting from the list of vulnerabilities to secure the software? Because initially this is what I tried to do. I looked into it and I couldn't. In fact, I got stuck at A1 injection, where we have OS injection, LDAP injection, XML injection, SQL injections, just to name a few injections. And each of them have its own defensive mechanism. So for me at the time, the question was, how can we, as developers, still write more secure software? And how can I explain it in very simple terms to my team of developers so they can use it while writing the code, in most of the times on the very tight deadlines? This list, the OWASP Top 10 Risks, is an awareness document which suits organizations and professionals that need to assess the state of a software, like, for example, pen testers, because it gives them a very nice checklist that they can assess the state of a software against it, but it's not for developers. So for me, the question was, how can we, as a developer, still write more secure applications? In particular, what are the security techniques that we can use while writing the software without being security experts? And still how to prevent these, the most common vulnerabilities? Because when these are in the software, these are some of the exploits that can take place. Like, for example, Mossack Fonseca or Panama paper, the latest one, Paradise Papers, which has touched every leader in the world. A vulnerability into a third-party library in HitChat, which allowed attackers to gain access to remote servers and steal users' information, customers' information. A vulnerability in Instagram's API, which has allowed attackers to steal users' personal information. An interesting one that might not be that well known, which happened in the software powering the slot machines in US casinos. And there the problem was that the numbers generated by that software were not random. This meant that it was easy to predict them. And this is exactly what the attackers did. By loading a sequence of numbers, analyzing them, they were able to predict the next ones, in this way increasing their wins. In fact, a team of 4 were able to win around $250,000 per week. And the latest one, Equifax. which has leaked data of million and million people around the world. So all of these breaches has in common the fact that they were breaches to the vulnerabilities in the software, and they happen at the application layer. And as developers, we write applications from enterprise applications, web services, or even a small website like this gorgeous little website with balloons and butterflies. Regardless of the size of the website we write, the question is how can we make it more secure? But where do we even start? A good starting point is the OWASP Application Security Verification Standard, or for short, ASVS. How many of you have heard of ASVS? Few, great. This document helps you to choose the right level of security for your own application, where level 1 is the minimum level. Every application should be verified at a minimum level 1. Level 2 is for those applications that in case of a data breach, okay, it's going to be embarrassing, it's going to create a little bit of a mess that needs to be cleaned up, but it's not going to be the end of the world. And level 3 is for those applications that you really do care about. Those applications that are really critical to the business. And in case of a data breach, well, there are going to be serious financial consequences. Those type of applications must be verified at level 3. And this is a good document because it helps both developers and managers within the business to have a common understanding of the appropriate level of security of their own applications. And here is an example of how the requirements look like, where each requirement is clearly marked if it applies to level 1, level 2, or level 3. Now, do you remember the breach that happened into the software powering the slot machines? So if, for example, the requirement 7.6 was taken into account, which says that all the random number generator should be created using the cryptographic module's approved random number generator, then that type of flaw could have been avoided. So we can use a document like ASVS that help us to choose the appropriate level of security for our own application. From there, extract those requirements appropriate for that particular level and use them in the software. Furthermore, we can use those requirements to generate the test cases that can help us to verify for security early and often. And this is control number 1, verify for security early and often. And when we say verify for security early and often, we actually mean that we should verify throughout the entire software development cycle, from the moment during the development stage using unit tests, code review. Before committing the code into the repository, you can perform further checks using the pre-commit hooks. And here you can add checks for sensitive data like secrets, token, passwords that must not be committed to GitHub or get into production. Further checks for deprecated algorithms like MD5 or dangerous functions like eval or exec. In fact, I had a developer that kept committing debugging messages into the production code. Not only that it produced error, but also it was a case of disclosing information. The simple way we dealt with it was to add it to the list of forbidden functions into the pre-commit hook. Once the code is into the main branch, here you can use the tests that have been generated from OWASP ASVS as functional tests. You can create Selenium tests in conjunction with WASP, ZAP, or other tools. And also at this stage, you can actually have tests using static analysis tools. Prior to deployment, you can run your regression suite of tests in conjunction with dynamic analysis tools. So control number 1 helps you from the start, not as an afterthought, to prevent all the OWASP top 10 risks. This control gives you a very nice framework where rather than thinking of security as an afterthought, You start with the requirements from the beginning, and instead of testing for security at the end of a project or project phase, you incorporate security testing into your software development cycle. And when possible, make it part of your continuous integration and continuous delivery. Great, what else can we do? What about this? 2017, and we still have cases of SQL injection. So this works by tricking the SQL parser and interpreting the input as part of the SQL command. The defense for this is Parameterize Queries. This helps untrusted input from being interpreted as part of the SQL command. But it's important that if we use this, then we bind to the variable. And this is an example in Java where not only that we use the prepare statement API, but we create the SQL command with a placeholder and then bind the variables to that placeholder. In this way, the actual defense happens at the SQL parser level. From that point on, the parser will treat those variables as simple strings. And using control number 2, parameterized queries, can prevent injections, most types. And we'll see further which types of injection cannot prevent. The next type of vulnerability, cross-site scripting. And unfortunately, the cross-site scripting is not given the required attention. And there have been in the past exploits where from a simple script, injection script like this, that loads the cookies of the user browsing that page and sent to a remote server, entire system were able to be brought down. In the case that the user browsing that page is an administrator, in that case, the attacker also gets access to administrator privileges. So there have been attacks all started from this humble cross-site scripting. Now, in the case of cross-site scripting, we have to be aware that depending on where your dynamic data is within the HTML document, there are different types of injection payloads. So, for example, if your dynamic data is into an HTML element like PT, a P tag, or a div tag, in this case, you need to inject a script in order to trigger the script execution, like a script tag. Or another case, you can actually insert an image with an invalid source that when trying to load that source triggers the on error event, and that's when the actual injection starts running. In the case of URL, for example, you are already within a tag, so you don't need to inject a tag. In this case, you can trigger the script execution with a JavaScript. But if you are already in a JavaScript context, then you are already there. So the only thing you need is just a function that needs to be executed. One of the things that I see as a defense is our filters. We have to bear in mind that the filters are simple blacklists. They're not the best defense and they are not loved by security professionals, but they are absolutely adored by hackers because it is possible to bypass the filters. And one way to bypass them is to write the same thing in multiple ways. And this is what you can see in the JavaScript example. You inject the alert function, which is going to execute, but you can write absolutely the same thing using, in this case, HTML entities, and both of them are going to execute successfully. So for this type of defense, of vulnerability, the best defense is to encode your output. Encode it just before writing it to the HTML parser. Like we have seen on the cross-site scripting injection payloads, it's important to apply the right method for the right context. So if your dynamic data is into a URL or an HTML context, then you need to encode for the HTML context. If your dynamic data is into JavaScript, then you need to apply an encode for the JavaScript context. To do it from the scratch is not the simplest thing to do, so the best way to deal with this type of vulnerability is to use a library that has already been out there, designed specifically for this purpose. In the case of Java, the best library out there is the OWASP Java Encoder. It's simple to use. You can easily include it using Maven. Has no dependencies, and it's regularly updated and maintained. Also, it has a contextual method encoding, so you just need to use the right method for the right context where your dynamic data it is. And contextually encoding the output can prevent injection and cross-site scripting. What else? So back to our website. What are the things we need to protect against? What about the data? For this, we have control number 4, validate all data. And when we refer to data, we actually refer to all the data that comes via a GET or POST, including hidden fields, file uploads, HTTP headers, cookies, including data from the database. Because when we validate the data from the database as well, then you can prevent other types of injection, like second-order SQL injection. How many of you have heard of second-order SQL injection? Not many. Okay. Okay, so I'm going to go through a very simple example about this type of vulnerability. So the second-order SQL injection works when the injection payload is stored into the database, stays there dormant until it's used in other parts of the software. And that's when the exploit actually occurs. So let's consider that we have a case where we already have a user join into our application, but now we record another user. Let's say John single quote dash dash. This value will be stored in the database and is going to become the injection payload when used in other parts of the software. So let's suppose now that we go in other parts of the software, like for example, to change the password. And when changing the password for our initial user, the SQL command for changing the password can become from the initial one of changing the password for user John single quote dash dash to changing the password for a completely different user, because that input contains an injection payload, which has been interpreted as part of the SQL command. So we can say that we have successfully changed the password for a different user and have performed a second-order SQL injection. The best defense for this is to validate the data, including the data that comes from the database. And validating all the data, including the one that comes from the database, can prevent injection, external XML external entities, insecure deserialization, and cross-site scripting. Great, so let's see what else can we do. Our website, like many other applications out there, has pages, sections that are available for everybody, and sections that are restricted to certain users. For this, we have control number 5, implement authentication controls. The authentication control is a complex security control. In this presentation, I will just go through few best practices, like, for example, implement a secure password storage, use multi-factor authentication, have in place a secure password recovery mechanism, you transfer any sensitive data via TLS, and have in place well-designed error messages that do not disclose information about the users of the application. When it comes to error message, to password, to storing the password, we want to make it as difficult for the attackers in case the database is leaked. For this, we must use a strong cryptographic algorithm like password-based key derivation function 2, bcrypt or scrypt. When it comes to the actual password, the latest NIST guidelines, which have just been published this year, recommend to allow in the passwords all the ASCII characters, including space. We have to take into account that these days, more and more people have more and more passwords, and there is an increase of the password managers. So it's important to allow in the software the paste functionality. The password that is entered by the users ideally should be checked against a list of bad passwords. You can come up with this list of bad passwords by looking into the data from previous breaches and selecting the top most used passwords, to which you can add dictionary words and sequential characters like 1, 2, 3, ABC. When it comes to the actual length limit of the password, the minimal recommended is 8 characters, but we should help the user with password strength meters to choose a strong password, and should allow the user to enter passwords as lengthy as they want. If the passwords are too long, then there is a risk of denial of service. Also, we have to bear in mind that bcrypt will truncate everything that is over 72 bytes. To deal with these two problems, one way is to implement a strong hash, like 512, which is a modern hash and has a higher collision rate. So if we are to recap when it comes to a strong password storage, we should use a user-specific salt. To avoid problems like denial of service or truncation, we should hash the password with a modern hash and protect those with strong cryptographic algorithm like a password-based key derivation function to bcrypt or rescript. Depending on the nature of the application, a second-factor authentication is also good to have. I have to point out that SMS is not considered a second-factor authentication and is prepared to ban it from their recommendation. You should use a FIDO or a dedicated app. But if you are implementing a secure, strong password storage in your software, then it's important to be consistent and do it throughout the software. And this is an example from Ashley Madison website where they actually have used a strong cryptographic algorithm like bcrypt, but what they did next was that the same password the user would enter was also used for a fast login key. And this was stored with the deprecated MD5. As soon as this was understood, it was very easy to crack the passwords. Around 11 million passwords were cracked due to this flaw. Now, when it comes to error messages, it is important to design the error messages in such a manner that they do not disclose information about the users or their identity. And this is an example, and you can still find many out there, where the visitor is presented with one error message if the user is found in the database, and a different error message if the user does not exist in the database. So you don't need to be a hacker to figure out which is a valid user and which is not. So it's important that for both cases, the user exists in the database and the user does not exist in the database. The visitor is presented with the same HTTP header, 200, okay, and same HTML message. So like I mentioned, the subject of authentication is a complex one. In this presentation, I just focused on a few best practices. You can find more within the project. But this is a good start to protect against broken authentication. So until now, we have discussed about who is accessing the page. What about which pages are accessed? For this, we have control number 6, implement appropriate access controls. The access control to the right is a very complex, design-heavy security control. The best way to deal with this is to use frameworks that have already been incorporated with well-designed access controls. And using a framework with well-designed access controls can prevent broken access control. Great, so what else can you do? What about the data that is transferred between computers over the internet, or the data at rest? For this, we have control number 7, protect data both at rest and in transit. When it comes to data in transit, the best protection out there is still HTTPS, which helps with confidentiality, integrity, authenticity. We have to bear in mind that HTTPS by itself does not protect against certain scenarios of man-in-the-middle attack. To reduce some of those scenarios, we can add an extra header, and this is the strict transport security header. This is a browser standard, and what this does is once it is downloaded onto the user's browser. From that point on, any communication between that browser and the remote server is done via HTTPS channel only. So if the user now types into the URL location bar example.com, and this header has already been downloaded onto that browser, the browser automatically switches to the secure channel, and from that point on, all the communication is done via the HTTPS channel. When it comes to data at rest, the best control out there is still AES, Advanced Encryption Standard. We have to bear in mind that it's important to have in place a secure key management for the key used to decrypt data, and appropriate access controls and auditing in place. And having in place controls for both data at rest and in transit can prevent sensitive data exposure. Great, so what else can we do? What about the logging? For this, we have control number 8, implement logging and intrusion detection. Logging should not be used only for debugging and troubleshooting, but can also be used for application monitoring, compliance monitoring, and intrusion detection. When it comes to the intrusion detection, there are 6 types of events that can be considered good attack identifiers, like, for example, authorization and authentication failures, client-side input validation bypasses, whitelist input validation failures, obvious code injection attacks, like, for example, obvious SQL injection payloads or cross-site scripting payloads, and high rate of function use. For example, if a page has been requested a high number of times in a very short period of time. So some examples of these intrusion detection points are if your application expects a GET but receives a POST, then that's something that is an indication that somebody has tampered with that. Additional form or URL parameters also is an indication that somebody has tampered with that data, since it has left the client side until it has reached the server side. For example, somebody can add an extra URL like admin=1 or another form parameter like debug=true. If the input validation fails on the server side, despite the fact that there is a client-side validation, that's another indicator. A simple example is we have a form on the client, and the form has an input with a maximum length attribute defined in the form. However, when the string reaches the server, the length of that string is greater than the value defined on the client side. So this is another good indication that somebody has tampered with a string, since it has left the browser until it has reached the server. So ideally, you take an action and decide of what the software should do in this type of scenario. Or if the server-side validation fails for non-user editable fields, like, for example, hidden fields checkboxes. A good example is an e-commerce website, basket page, because on that basket page can be various interesting information, like hidden fields for price. That can be tempted even by us to actually start playing with that value. But if the value that reaches the server is different from of the price that was part of a hidden field, is different from what the software actually expects, then we should put in place a logging and give the software the ability to respond if this is the case. So from a software point of view, what we are doing, we are actually ensure that the data the software expects is the actual data that the software receives. When this does not happen, then using this intrusion detection point, we put into the software the mechanisms that allow the software to respond in real time and to minimize possible attacks or even stop them. And having in place secure logging in conjunction with a intrusion detection mechanism can prevent all the OWASP top 10 risks. Great. So what else can we do? Now, starting from the scratch, and to write a code for security control every time we write a new application or a new or a new web service, not only that is time-consuming, but can also lead to security design flaws and implementation flaws. Think, for example, of access controls. These are complex design, heavy security controls. You don't want to do them from the scratch. Or even a library to protect against cross-site scripting is not the simplest thing to do it well. So the way to deal with this is to use security frameworks and libraries that have been already designed with security embedded in. And this is control number 9. Leverage security frameworks and libraries. Not only that this saves time, but can also reduce the security design flaws and implementation flaws. For example, we can choose a framework with well-designed access controls and CSRF protection. We can bring a library to protect against cross-site scripting or an ORM to prevent SQL injection. But there is a problem out there at the moment. And the problem is that there is a lot of software with vulnerable libraries. In fact, in the case of Java, 88% of Java applications contain at least one component with one known vulnerability. And looking further into it, the main cause of this is the technical debt and the way it has been implemented in the beginning, incorporated these third-party components, these external libraries. So let's consider the following structure where we have our own code, but now we bring a package with a library that depends on another library that depends on another library. And now we start implementing functionality from this into our software, and we add that functionality from the third-party component into a module, then another module, then another module. Soon enough, functionality from third-party components touches your software into tens, hundreds, or even thousands of points. In the case of cross-site scripting, it can easily go into thousands of these points. And now a vulnerability is reported, and might not be in a primary library, might be in a dependent library. So in this structure, it's very difficult to understand, first of all, what's the impact of that vulnerability in that dependent library, and then what are the best controls that we can put in place? Okay, so if we have agreed on the controls, then how long do you think is going to take a developer to go through hundreds or thousands of places to change the code? And how long is going to take the tester to change to test all those changes? In fact, I had a team with this type of structure, and it was a case of cross-site scripting. And the developer has implemented all those changes into hundreds of places. And during the QA, they have discovered that the software didn't work as expected. It was a French-Spanish website with special diacritical characters. And in certain parts of the application, those did not work correctly. In panic, the developer rolled back all the changes, and they were back to square one. So just by bringing in libraries, but not incorporate them and not manage them correctly, the software is at risk of being breached through vulnerable components. We have to bear in mind that an attacker would not try to break into the nicely developed software when they can achieve the same thing with much less effort by breaching into one of these vulnerable components that have been brought into the software. And it's important to understand that when we refer to vulnerable components, we actually refer to those vulnerabilities that are publicly disclosed on national vulnerability database available for everyone to see, understand, and understand how to exploit. So this is the reason why these publicly disclosed vulnerabilities are easy to exploit and very easy to automate as well. So the question is, when we bring in these third-party libraries, how can we do it? What is the best way to actually implement this? Well, a good start to answer this question can be found into Robert C. Martin's book, Clean Code. How many of you have read the book? Okay, this is what I expecting, a few hands. Excellent. And what he says there is that by wrapping the API, you minimize your dependencies. And if you want to change the library in the future, this can be done without much penalty. So these are some benefits from a software design point of view. There are further benefits from a security point of view. We have to understand that in the world of security, there is a continuous cat and mouse chase between the developer and the attackers. The developer writes a library, the attacker breaks it. Developer fixes, the attacker breaks it again. So it's important to be in a position where we can upgrade these libraries easy. And in the case that the library has become obsolete, it hasn't been maintained for years, then we can replace that library without much penalty. Apart from this, there are further benefits. By wrapping your API, what you actually do, you document of what you use and how you use it. Not only this, but you expose into your software only the functionality that you require and hide unwanted behavior. In this way, you reduce your attack surface. You just leave into your software only what your software really needs. If a vulnerability is now reported in this scenario, then you have the wrapper that documents of what is used and how it's used. And this is the one place that allows you to change your code. And if the implementation is done as recommended in Uncle Bob's Clean Code book, which it has a very nice chapter, The Clean Boundaries. And if you also have tests for the functionality exposed into the software, then you can also quickly check your changes and how those changes affect your software. Now, depending of the complexity of the library that you bring into your software, there are a few software design patterns that you can consider. If you are just using a simple library, then you can use a simple wrapper to expose into your software only the functionality that you need and hide unwanted behavior. In this way, you reduce your attack surface. If you need to convert from the required interface to the provided interface, you use the adapter. And if you have a complex subsystem, then you can use the facade design patterns that helps to simplify the interaction between your software and a complex subsystem. Now, when it comes to the number of these components, for even a normal application, not even a large one, it can easily go into tens or hundreds of components within an application, especially in Java. So to try to monitor all of these components on a manual basis, it's impossible. So the way to deal with this is to automate the checks for these components. Now you can use commercial tools, which are out there, but you can also use free tools, like OWASP dependency check. How many of you have checks for their components, external components? Quite a few. Okay. So if you can't afford the commercial tools, you can use the OWASP dependency check. This has support for .NET and Java. And how it works, it actually looks at the libraries from Maven and then searches on the National Vulnerability Database, NVD, to find out if there are any vulnerabilities reported against those components. So when we leverage libraries, if we are to sum up, then we should do it. We should use those libraries from trusted sources. And when we bring them into the software, we should encapsulate them, expose into the software only the functionality required by the software and hide unwanted behavior. In this way, we reduce the attack surface. It's also important to regularly check them and regularly upgrade them. Or if they have become obsolete, you should replace them, which should be done without much penalty. and leveraging security frameworks and libraries, but doing it in such a manner that the software is safe and stays safe throughout its life can prevent all the OWASP risks. Great, and the last control, error and exception handling. Now, when it comes to errors, a good rule of thumb is that all the errors and exception handling should be directed through a centralized routine. The error should be verbose enough to explain the user the issue, but should not give information about the application. As an analogy, think of the coordinates. By themselves, the coordinates, latitude and longitude, have no value. But put them together and they can pinpoint the exact location on Earth. So the same is valid for the error messages. One error message by itself might not mean much, but one of the things an attacker would do is to poke around the application and see the responses the application it gives, then aggregate all of those messages, and from that aggregation of data, extract information about your software, the business logic within the software, the environment which server it sits on, which database is behind. So it's important that we don't leak information about our application. One way to deal with this is to give the user an error code and then log into the database, the actual error message, or if you still need to display the user a message, then have all the messages centralized into one place, like a config file or a database. This will give you the same bird's eye view like an attacker, and it helps you understand if you disclose too much information about your application. And having in place well-designed error messages that do not disclose information about your application or its environment can prevent all the OWASP risks. Great, so let's go back to our website. And let's recap which are the controls that can take developers on the path of secure software. So we can start with a document like ASVS that help us to understand what's the appropriate level of security for our own applications. From there, extract the requirements appropriate for that particular level and use those requirements to generate the test cases that can help us to verify for security early and often. We parameterize all the queries, but we bind the variables, and this can prevent injection, most types. We contextually encode the output, and this prevents injection and cross-site scripting. And we validate all the input, including the one from the database, which can prevent injection, including second-order SQL injection. XML external entity insecure deserialization and cross-site scripting. We implement appropriate access controls, authentication and access controls. We protect the data both at rest and in transit. We implement logging in conjunction with the well-designed intrusion detection system to give the software the mechanism to respond in real time to possible identified attacks. For complex security control, we leverage security frameworks and libraries, but do it in such a manner that we ensure that the software is safe and stays safe throughout its life cycle. And we have in place well-designed error and exception handling that does not disclose information about the user, the application, its environment, its business logic. So what I would like you to take away is that using these controls can help you to build a more secure application. But it's important to use them in a consistent manner, continuously. We have to remember that an attacker needs one flow to bring down an entire system. So using those consistently throughout the software is equally important as using them in the first place. Now, if you'd like to know more about the project, you can have a look at the OWASP project page for the OWASP Top 10 proactive controls. And you can also find us on Twitter. Thank you very much. Do you have any questions? Yes, please.
When you use third-party libraries, how much risk is there that somebody gives you another one by being third man in the middle in the development process, and you think you use a touch library, but you use Al Capone library instead?
Well, in the case of Java, you would bring them from Maven. Then there is a less risk to actually be corrupted. I can't say it can be 100% sure, but in that case, what you have is the MD5 of that component, and that is what actually the tools are checking for vulnerabilities. So they are checking against the hash for that component that you get from Maven. If you download that component from a website, then you don't know what actually contains that component. So it's good to, in the case of Java, use from repositories like Maven, because that's what the tools are using as well to check for vulnerabilities against databases of vulnerabilities.
But still MD5, not SA.
MD5 is the signature of the file. Yeah. Any other questions? Okay, thank you very much.